part 2 of this screencast. I want to finish up this problem. So we had on the last video had dissociated the base, and since it was a strong base, we said that it dissociates 100%. And if you were looking at that last video lesson, I did point out that 2 hydroxide ions were formed. Now, rather than to go back through that whole entire spiel, I'm going to pick up where the video cut me off. So what we had done at the equilibrium when we iced our problem, we had none of the original base molecule left. We had 1.0 times 10 to the negative 5 molar of the magnesium ion. But since we're looking for the pH, we need either the H or the POH to get to that. So here's where I said we had 2 times the 1.0 times 10 to the negative 5 molar. So that means that the hydroxide ion concentration here is actually 2.0 times 10 to the negative 5 molar. So here is the concentration that we need. So now we can find the POH by taking the negative log of the hydroxide ion concentration, which is negative log, in this case, of 2.0 times 10 to the negative 5. 2 sig figs here means I need 2 decimal places in my POH. So for my POH, I get 4.70. That's your POH. And so that means that the pH is equal to 14 minus 4.70. I need 2 decimal places here. So we get a pH of 9.30. So again, we have a basic solution, and I always make sure that the answer makes common sense. If you're dealing with a strong base, you should have a basic pH. So what if it's a weak acid or a weak base problem? How do we handle that? Well, step 1 would be to write the dissociation equation. So write the chemical equation for the dissociation. Now, since it is a weak acid or weak base, instead of assuming 100% dissociation, we're going to assume equilibrium, and we're going to assume that only about 5% dissociates, because that's what happens with your weak acid and weak bases. Step 2 is to ice your problem. Set up your table. Write your law of mass action. Determine your shift in terms of X. And remember that X is, in this case, is going to be either the hydrogen ion concentration if it is a weak acid, or it will be the hydroxide ion concentration if it's a weak base. So you'll solve for X. If your X is the hydrogen ion concentration, you will then take the negative log of that to get your pH. Now, if your X is the hydroxide ion concentration, you would take the negative log of that to get your POH, and then you would have to subtract from 14. Now, there is one little shortcut that I want to share with you for these weak acid, weak base calculations that we can use, and it's called the 5% rule. This is a really handy shortcut when it's a weak acid or weak base, because we do know that weak acids and weak bases only dissociate about 5%. So there are certain times that we can neglect the X in our problem. So this greatly simplifies our calculations when we can invoke the 5% rule. So what is the 5% rule, you may ask? Well, the 5% rule is when you have an initial amount of the substance present when you ice your problem. So in the initial, you have an amount present. If underneath that in the change column or row, there's an X, you can actually neglect the value for X because it's going to be so small with these weak acid and weak base problems. And at the end, you just have to check and make sure that the X is less than or equal to 5% of the initial amount. As long as X is less than or equal to 5%, then neglecting X is allowed. So the 5% rule is also referred to as percent dissociation. So this is a little formula for those of you that like to have formulas to refer to. that you could use to calculate the percent dissociation or the 5% rule. And again, if the answer you get for the percent is less than or equal to 5%, then you're neglecting X as allowed. So you take your X value, usually it's your hydrogen ion value concentration, divide it by the original acid concentration, and then multiply by 100. As long as it's less than or equal to 5%, you can neglect X. So let's take a look at a weak acid problem. This wants us to find the pH of a 0.50 molar solution of acetic acid, which is one of our weak acids. And notice here a difference is on these problems, you'll be given a Ka, or if it's a base, a Kb value. We still do the same steps. So write your chemical dissociation, HC2H3O2. And here we're going to use equilibrium symbols. This will dissociate into the hydrogen ion and the acetate ion. So we're going to ice our problem. ICE. So it tells us that initially we have 0.50 molar of acetic acid. So right here I'm going to put 0.50 molar and 0, 0. Now, since this is an equilibrium and it's a weak acid, we're going to determine the shift in terms of X here. It's not 100% dissociation, so minus X. This is a 1-to-1-to-1 ratio, so the coefficients are 1 here. Now, the products is where it shifts to because there's a hole, so plus X plus X. All right, so write the law of mass action. Ka is equal to hydrogen ion concentration times the acetate ion concentration divided by the acetic acid concentration. Now we're given the Ka, and in terms of X, 1.8 times 10 to the negative 5 equals, now here's where we can invoke the 5% rule. You see how we have an initial amount present of our acid? Since it's a weak acid, or if it were a weak base, you can neglect the X. So we can assume this is so minimal, it's not going to really change it. So we're just going to leave this 0.05, and that means here, this will be X and this will be X. So let's plug in these values into our law of mass action. So for hydrogen ion, we're going to put X. For acetate, we're going to plug in X. And here, we're going to plug in 0.50. So we've neglected the X here. But at the end, we're going to check for the 5% rule. That's very important that you always double check it, because if it's more than 5%, then you will have to go back and plug in the minus X here and then solve it like we did with our equilibrium problems from the last unit. All right, so now we're going to cross multiply here. That's going to give me 9.0 times 10 to the negative 6 equals X squared. Now you may want to pause the video and solve for X here on your own and then pick up. I'm going to go ahead. Now to solve for X, we're going to take the square root of both sides. And that's going to give me here 3.0 times 10 to the negative 3 molar is equal, and I'm going to put a little squiggly because that means approximately, because we are neglecting X. It's approximately equal to our shift. And also remember, X does represent the hydrogen ion concentration. So this will be hydrogen ion concentration if, in fact, we can neglect X. Let's check the 5% rule real quick. For the 5% rule, you take your X value, which is 3.0 times 10 to the negative 3, divide it by the original acid, 0.50, and multiply by 100. Now, as long as this is less than or equal to 5%, then you can neglect the X and you can move on with the rest of the problem. So we're going to say 3.0 times 10 to the negative 3 divided by 0.5 times 100. When you plug that in, we get this is 0.60%, and I did multiply that by 100. So this is the 5% rule checks out, so we can neglect X. So that means we can use this as our hydrogen ion concentration. So the pH is equal to negative log of H. Substitute in here, negative log of 3.0 times 10 to the negative 3. We have 2 sig figs here, so we need 2 decimal places.